I believe this is page 7 of your unit handout. Once again, I did my best to double check things, but I've changed this unit considerably from what it's been over the past few years. So if you see discrepancies between what's in your handout and what's up here, please let me know. We're into chapter 10 now, and we're going to be dealing today with sums and differences of functions, tomorrow with products and quotients of functions, and then Monday with something called function compositions. So what we're looking at doing today is sketching the graph of a function that's the sum or the difference of two functions. And ultimately, everybody, it doesn't matter what the graphs are. What I'm saying is if I give you a graph of f of x, and you see the graph, and I give you a graph of g of x, and you see that graph, and I say, what does the graph of the sum of the functions look like? That's what we're learning. What does it even mean to say the sum of two functions? Well, we will learn about that. I really want us to focus here in terms of domain and range on domain, because, and I can tell you this right now, I don't even think we're going to be worried about finding any ranges in this example. And the reason is this. We're going to come up with what's called a domain rule, where you can look at functions that are separate and tell me what the domain will be when we put the functions together. There's something called the domain rule. There is no range rule. To determine a range, you need to look at a graph. That's not always true. Sometimes you can look at the equation and sort it out. But I don't want us to focus on range here today. And then we're going to be working with function notation and equations of functions. So to begin with, some definitions. And this is more about language and how we write things on paper. The sum of two functions can be written as, and listen to how I say this, the sum of two functions can be written as f plus g of x. I'm not saying f plus g of x. I'm saying f plus g of x. And I know it seems very goofy because all it means is f of x plus g of x. And the sensible student would say, well, why bother? Why not just write f of x plus g of x? And the answer is, I don't know why. Okay? It's a language that we need to learn, though. And the difference of two functions is written as f minus g of x, and it means f of x minus g of x. Before we go on, does the order in which you add things together, whether they are numbers or anything else, does the order in which things are added change the outcome of the sum? No. 3 plus 4 is 7, 4 plus 3 is 7. Does the order in which you subtract quantities change the outcome? Yes. So I'm pointing out to you, and you can add this if you like, that f plus g of x is equal to g plus f of x. They're the same. But f minus g of x is not the same as g minus f of x. And I know it might be too early to ask you this question, but if I tell you that f minus g of x is a graph, is a function, that when you subtract two functions, you get a new function. If I tell you that f minus g is a function, and sometimes I will say f minus g, and that's okay. Sometimes we will even write that, and that's okay. But if I tell you f minus g is a function, and I tell you g minus f is a function, but they're not the same function, does anybody know how they're related? Brooke? Not inverses. We're kind of along the right track. Alex?
Would they be reflections of each other?
What kind of reflection?
Vertical.
They would be vertical. And if you can wrap your head around that just out of the gate, you will start to appreciate that this is all going to be about y coordinates. Okay? That will be the lesson you want to learn here. So if you wanted to, I could make this a true statement by putting a single line, and I could put the single line through the equal sign, or I could put a negative in front of that. And as we get deeper into the lesson, you'll understand why that's the case. Again, this is going to all be about y coordinates. I believe in your handout this says warm up, correct? Okay. So this is warm up number 1. We're considering two functions. One function is f of x equals 2x plus 4, and the other function is the absolute value of x plus 1. And I do want us to draw fairly decent graphs here. Both of these functions have linear portions to them, and I'm choosing this as opposed to quadratic because then we can draw very precise. If you have extra rulers, just leave them at the back. Draw very precise graphs. I don't want to worry about curviness or anything today. There you go. Oh, one more. One more. Thanks. So, first thing we are asked to do is determine the equation of f plus g, quantity of x. So sometimes I will say instead of f plus g of x, or instead of f plus g, I will say f plus g quantity of x. Well, h of x here is simply equal to f of x plus g of x. In fact, I would argue or say to you that when you see this, your brain should already have translated it to f of x plus g of x. And we look up here and we see f of x is 2x plus 4. G of x is the absolute value of x plus 1. We can simplify that a little bit, like the 4 and the 1 add together to give 5. And that means the equation of the function h of x is, it doesn't matter the order that you write these things in. I'm going to write 2x plus the absolute value of x plus 1. I could write, plus 5. I could write the absolute value of x plus 2x plus 5. I could switch the order of these things. This is not an exam question. You would be so lucky to get a question on a diploma exam that said this. You wouldn't. You might get a question that you had to do this as part of your solution, but this is not the question. We're learning about things here. Sketch the graphs of f of x, g of x, and h of x on the same set of axes. So I have filled in a table of values here, and this is not just about you constructing the graphs, and we are not using our graphing calculators. This is about listening carefully to my explanations about what's going on. Okay? So I hope everybody understands how I filled in the column for f of x. What I've done is I've taken an x coordinate of 4, and I've put it in here, and I've calculated y. And then I've taken an x coordinate of -3, and I've put it in here and calculated y. And the thing I want to impress on you, because of that, is that this column, although it's called f of x equals 2x plus 4, this column is the y coordinate on f. That's what those numbers are. They are y coordinates on f. Let's sketch y equals 2x plus 4. We're not going to use the table of values. You should know that the function y equals 2x plus 4 has a slope of 2 and a y-intercept of 4. You should know it's a linear function. So on our graph, I'm just going to lay down a few lines here. So on our graph, y equals 2x plus 4 will have a y-intercept of 4, and it will have a slope of 2, which means you go to the right 1 and up 2. And you can choose to put in a number of points if you like. Bottom line is you need to lay your ruler down. And I would ask that you do a fairly decent job of this, meaning I should be able to go down to the bottom and see the x-intercept here is -2. So if I were to use all of the space that I've provided to you for the graph, we want a nice, precise line going through those points. Are we okay with graphing that? Okay. Now, what about the absolute value of x plus 1? I just want to talk about this function. Well, you have all of the skills in your arsenal needed to graph this, because you know what the absolute value of x looks like from Math 20. Please don't draw this, because it's not the function. But the absolute value of x looks like that. That's not the absolute value of x plus 1. That's the absolute value of x. We're not using the table of values to graph this one either. We're just using our knowledge of math. The table of values is there for a different reason. Well, the absolute value of x looks like that. The absolute value of x plus 1 will be that shifted up 1. That's all. And I'm using very basic functions here. Because I don't want us to get bogged down in the details of each of these graphs. That's not what's important. So this is shifted up 1. And again, I would like you to do your level best to sketch this as perfectly as you can so that it's going through the proper points. I'm hesitant in labeling those graphs because I don't want to clutter up the visual. I think you can look at that and understand that the red graph, even though you didn't use red colors necessarily, that the red graph is the linear function and my orangish graph is the absolute value function. So are we all settled into this? We've got this fine. Now let's go back to the table of values. See, how did I determine this column? Well, what I did for the middle column is I took -4 and I fed it in for x here. And I took the absolute value of -4, which is 4, and I added 1 to get 5. And then I put in, say, -2, and the absolute value of -2 is 2, plus 1 is 3. So I've populated it that way. But what I would like you to understand is that this is the y-coordinate on G. What I would like everybody to do now is I would like you to populate the empty column in the chart. I want you to calculate what h of x is when x is -4, when x is -3, when x is -2, etc. And write in the numbers. And to interrupt you, and I apologize for doing so, how many of you are just doing it? You're not doing any real big calculations here. Why is that? Because the third column is f of x plus g of x. This absolute value of x plus 2x plus 5 is the sum of 2x plus 4 and the absolute value of x plus 1. In other words, it's the sum of those two columns, so this will be the y-coordinate of f plus the y-coordinate of g. You do not need to calculate anything on your calculator. You just add these numbers together. And you know me, my brain kind of squeals around a bit sometimes in the wrong direction. Are those numbers sums correct? Okay. And once again, everybody, I'm trying to teach you what's going on here. That when we graph this third function, the sum of these two, we're not going to use a table of values. This table of values is there to teach us that the y-coordinate of the sum of two functions is found by taking the sum of the two y-coordinates of each function. But, and this is the final piece of the puzzle, yes, the y-coordinate on h of x is the sum of the two y-coordinates, but the x-coordinate stays the same. I'm going to show you a way of writing this with mapping that I made it up. I don't know if you want to use it on a diploma exam or not. I think it makes sense, but I've never seen it. When we go from f of x plus g of x, and we start talking about points, this is the mapping. That's the mapping. The x-coordinate stays the same. All we're doing is we're looking at a particular location for x, and we're saying, let's add the y-coordinates. So you look at x equals 2, and you add the y-coordinates to get the y-coordinate at 2. And again, I haven't seen this, but I think it communicates, this is a plus, I think it communicates the idea well. I think you understand what I mean. So how are we going to graph the sum of these functions? We're not going to worry about the equation. We're not going to worry about the table of values. In fact, I will go so far as to tell you that you shouldn't even know the equations of these two functions to be able to graph the sum. I should be able to graph, with my eyes closed, two random functions and ask you to sketch the sum of those two functions. And all you do, and I need to grab a blue marker. I hate blue. Okay, so all we're doing is we're looking, say, at this x-coordinate here. Don't mess up your graph. I'm just indicating we're looking at -4. And we're reading the y-coordinate down here of the red graph, and it's -4. And we're reading the y-coordinate of the orange graph, and it's 5. And we're taking -4 plus 5 to get 1. That's all we're doing. Then we're moving over, and we're looking at -3. And we're reading at -3 a y-coordinate of -2 on one function and a y-coordinate of 4 on the other, so we add those two y-coordinates to give 2. All of these little marks are just me explaining to you what I'm talking about and where I'm looking. I have a question for you. To how many of you does it make sense that if you were to add two straight lines, you're going to get a straight line? They're not linear. One of them's linear, one of them's absolute value. Let's continue. If I were to look at x equals 2, then I add 0, which is the y-coordinate here, plus 2, which is the y-coordinate. 0 plus 2 is 2. Now, I admit you didn't have to do this because you do have a table of values, right? And I misspoke there. You add the y-coordinate of 0 plus the y-coordinate of 3, giving you a y-coordinate of 3. Let's continue and see what happens. At -1, each of the y-coordinates is 2. and I add 2 and 2 to get 4. At 0 for x, I'm adding negative 1 and 4. What's negative 1 plus 4? Or sorry, 1 plus 4, I get 5. Still in a straight line. If I go now and I look at 1, I'm looking at a y-coordinate of 2 and a y-coordinate of 6. 2 plus 6 is 8. Something changed here. And it's changing because, and I don't know if this will be helpful, it's just the thought I have. It's changing because up to that point, those two lines are each straight. And then after that point, one of the lines continues, but the other line changes direction. What the graph looks like in the end is not the lesson. The lesson is you're adding the y-coordinates. So we can do one more point. I think we might have enough room for one more point. When x is 2, y is 3 on one and 8 on the other, and 3 plus 8 is 11. Let's add one more. When I go to 3 for x, we can add a couple more. I'm going to add the y-coordinate of 4 and the y-coordinate of 10, which will give 14. And I think we have to stop there because the last one will be off the grid. So what does this graph look like? Looks like that. Don't try to read any cosmic significance into the shape of that graph or try to figure out why it looks like what it looks like. It looks like what it looks like because you add the y-coordinates together. I'm going to pause there and just before we wrap up this first part of the warm-up, because there's another one for subtracting, but I think we can go a little quicker. Does anybody have any questions about what's happening when you're adding two functions together? I guess now that everything is on here, you can label these. This is f of x. I'm not going to use colors here. This is g of x. And this blue one is h of x. And again, I think what I said earlier is important for you to know or understand. What the original two functions look like is of no significance. Well, it's not important how you get those graphs. I could just randomly draw two functions on a grid and say, draw the sum of the functions. Your goal is not, everybody, to, if I showed you these graphs, the red and orange graphs, your goal is not to try to figure out what the equations are so you can add the equations so you can graph it on your calculator. All right, let's move on. What is the domain and range of h of x? I believe, on your handout, does it say domain and range? It does, okay. So the domain is x is any real number. You can see that by looking at the graph. The range is y is any real number. I don't care about the range. What's important is the domain. And you might wonder at this point, what's the big deal? Let's focus on the domain. How are the y-coordinates of the points on the graph of h of x related to the y-coordinates on f of x and g of x? We've already said this, that for any particular, I won't do that yet, for any particular pair of points that have the same x coordinate on f of x and g of x, they combine to produce a new point with the same x coordinate, but whose y coordinate is the sum of the 2 points, the 2 y coordinates. In the past, prior to me thinking of a way to communicate this, I would have just said this. And as far as it goes, that's fine. except it doesn't really tell you that the x coordinate is staying the same. You're looking at a single value of x and adding the y coordinates. All right. This will say warm-up 2 in your handout, I believe. Okay. So now we have two functions. F of x equals root of x minus 1. G of x equals x minus 1. Determine the equation of the difference between the two functions. H of x will be equal to f of x minus g of x. So h of x is the square root of x minus 1 minus x minus 2. And if that's all you write, it's wrong, obviously. You need a set of brackets. Whether you choose, I think in my table of values I left it that way. But on paper, you would probably get rid of those brackets and say h of x equals root of x minus 1 minus x plus 2. And there's nothing you can do to simplify that, because you have a radical, you have a variable, and you have a number. How many of you see exactly where this is going? That what we're going to do in this warm-up is the same thing as what we did in the previous one, except we're subtracting functions. So briefly, I populated the second column of this table by putting those x values in for x in f of x. So for example, negative 1 in here gives me the square root of negative 2. Not allowed. By the way, you could make an observation that x minus 1 must be greater than or equal to 0, which means x is greater than or equal to 1. And that means you can't start populating the table until you get to x equals 1. Similarly, I hope you understand what's happened to populate the g of x column. I've taken these x coordinates and I've popped them into x in the second column. So the point needs to be made that this column is actually the y coordinate of points on f of x, and this is the y coordinate on points on g of x. So we do not need to spend time populating the table. That's not what you're learning. You could populate that table in grade 9. I hope you understand, and I'm going to explain this in a slightly different way, that since this is the y coordinate on f, and this is the y coordinate on g, then that third column, the fourth column actually, but the final column, is simply the y coordinate on f minus the y coordinate on g. And it occurs to me that, oh, I did complete these. I thought maybe I forgot to complete them, because it's such a simple task. So we can put at the top of this that what this is the y coordinate on f minus the y coordinate on g. And I'm going to start at the bottom here, everybody. 2 minus 3. Root 3 minus 2. We could figure out what that is. It's approximately negative 0.27, I think, but that's neither here nor there. When we need that decimal, we'll get it. Root 2 minus 1. 1 minus 0. 0 minus negative 1. Now what are we going to put for a y coordinate on the final column when x is 0? Well, if you look at the equation for the final column, it contains the square root of x minus 1. So you can't do it. But I want you to think of it differently. We need to take this and subtract that. And the bottom line, everybody, is you cannot subtract two things unless they both exist. You can't subtract things unless you have two things to subtract. And I know it amounts to the same thing, but basically, the third function will only exist x-wise wherever both functions exist. Over here to the left of 1, where that first function doesn't exist, it makes no sense to talk about the sum of the two functions. So we're going to put undefined, undefined. We are not going to graph these functions using the numbers in the table. The numbers in the table are there to convince you that h of x is a series of y coordinates that are the differences of the y coordinates of f and g. So let's sketch these. If I start off with root x minus 1, just bear with me, don't draw anything yet. You should know that root x looks like this, way back from unit 1. It has a vertex, I suppose we can call it, at the origin. It's not a vertex like a parabola. You go up 1 and over 1, you go up 2 and over 4. But this minus 1 with the x means we've shifted it 1 to the right. So this is what root x looks like. And unfortunately, in order to make my point with regards to domain, I had to go away from straight line graphs. So you have to draw this curve. Oh, and that was perfect. I was right on track. What a ripoff. Let me try that again. Oh, that's still pretty good. So that is f of x, and we can label it later. G of x is x minus 2. Well, that's pretty easy. That's a slope of 1 and a y-intercept of negative 2. My colors here may not match the f, g, and h that I had in the previous question. I know I should have arrowheads on the ends of that, but I just couldn't be bothered. So what about this third function? We're not going to look at the table of values. We're not going to look at the equation. We are going to say it's the y-coordinate of f minus the y-coordinate of g. So if I tell you to look over here at x equals negative 5, and I say, what do you get when you take the y-coordinate on f and you subtract the y-coordinate on g? I want to just fix something here. What happens when you take the y-coordinate on f of x and subtract the y-coordinate on g of x when x is negative 5? Well, the answer is you can't do it. I'm asking you to do something that's not possible. And if I say, go ahead and subtract the y-coordinates of the 2 points when x is here, you can't do it. You can't subtract things that don't exist. Even if just one of them exists, that's not enough. And if I say, subtract the y-coordinates when x is negative, sorry, I totally misread this. I said negative 5 here, didn't I? It's negative 1. Do you remember me saying negative 5? It's negative 1. I don't know why I think I was looking at this as being negative 2 here. Anyway, can I subtract the y-coordinates at this location for x? No. But I can start subtracting them here. And you have to be careful because order of subtraction is important. I'm going to take the y-coordinate on f, which is 0, and subtract the y-coordinate on g, which is 1, giving me 1. Then I'm going to move on, and I'm going to take the y-coordinate on f, which is 1, minus the y-coordinate on g, which is 0, and get 1 again. You still with me? I'm going to move on. I'm going to go over here. And here's where things get a little bit awkward. This y-coordinate, I'm going to read it from the graph. We could go back and say, I believe it's root 3 minus 1. Doesn't matter. Do you agree that's approximately 1.6-ish for a y-coordinate on the red graph? I can tell some of you want to just say 1.5. Okay, I'll go 1.6 minus the y-coordinate on the orange. 1.6 minus 1 is 0.6. So now all of a sudden this graph is dipped down. Here's a very interesting point. What will happen here for x equals this point? What will we get for a y-coordinate? 0. When they intersect, they have the same y-coordinates, so when you subtract them, you're going to get 0. Whoops. We can do one more over here. 2 for the y-coordinate at 5 minus 3. 2 minus 3 is negative 1. Good? We need to explore what happens between those first two green points. And I might even recommend actually calculating what the y-coordinate is on this function when x is 1.5. So that's what I would like you to do. Put in 1.5 for x, and I want you to calculate what h of x is. And when somebody has the number, let me know. No? Jay, do you have it? 1.2 approximately. Can I get a couple other people to agree? So, you know, sometimes we have to dig a little deeper. This actually goes up a bit. So this is what the function looks like. And I'm just going to erase that last part and just say that's what the function looks like. Any questions with constructing the graph, particularly in regards to the fact that we're subtracting y-coordinates to generate a series of new points? All right. What is the domain of h of x? I know it's obvious by looking at the graph, but I want to illustrate what's very important here. That if you were to take a look at g of x, and I'm just going to go back to make sure I have my memory right. G of x was x minus 2, so the domain of g of x is any real number, right? G of x is defined everywhere. What is the domain of f of x? Well, the domain of f of x is x is greater than or equal to 1. So what is the domain of the result of subtracting two functions? It's going to be the domain that they have in common. We talk about a common domain. And this colors are meaningless. I'm just picking different colors. F and G are both red here, but this is the important thing, that h of x is the domain that's common to both f and g, so that's the domain. The answer is that. And it may seem like an obvious thing, but there's a rule for it that we need to follow. All right, so how are the y-coordinates related? Well, you take the y-coordinate on f and you subtract the y-coordinate on g to get the y-coordinate on h. So what have we learned in the warm-up? We've learned that it's all about y coordinates, and that a domain of a sum or a difference is the domain that's common to both. That's the warm-up. And my hope is that by going slow with the warm-up, the examples are easy now. They really are. Consider these functions. We've got 4 functions, and I'm saying to you, write the equation of g plus f of x. Well, g plus f of x will be equal to the sum of g of x plus f of x. There's nothing to do here. You're adding the functions together, and you're getting x squared plus 2x plus 2. This is the new function. You can call it h of x. Better not call it h of x. You can just call it y if you like. What is the domain of that function? Well, I know that many of you will look at that function I've just written and say it's a parabola, so the domain is any real number. But the reason the domain is any real number is because the domain of this function is any real number, and the domain of this function is any real number. So they overlap everywhere. F minus g, well, f minus g of x is going to be 2x plus 4 minus x squared minus 2. Simplify it. And again, the domain of the difference of these two functions will be any real number because they both have those domains. So what do I get? A negative x squared, a positive 2x, and a positive 6. Any questions with A and B? Did I do my arithmetic right there with the numbers and the brackets and the negatives? Good. C, h plus I. Well, this is almost laughable because there's nothing you can do here. Right? There's nothing to do with that. Let's do I minus g while we're at it, and then we'll do the domains. I minus g will be, do you have I minus g? Or do you have an I of x up here? Which one is I? The last one? Okay. It's funny how I didn't even notice that when I did C. But this is an I in your handout. Yes? Okay. So this one will be I, which is log base 3 of x, minus x squared minus 2. And when I subtract x squared minus 2, I subtract the x squared and I subtract the negative 2. So what are the domains? Well, the domain of this is x is greater than 0. You should know that from the previous unit because one of two ways to look at it. You either can't take the logarithm unless it's greater than 0, or there's an asymptote there. This one, you're going to say 24 minus 2x is greater than or equal to 0. So x is less than or equal to 12. Are you with me on that? That I solve it for x, but then I have to write it the other way. So what's the overlap? Think carefully about this. What's the overlap between me saying x must be greater than 0 and x must be less than 12? Well, if we were to sketch it, here's 0, and I'm saying x has to be greater than 0. Here's 12, and I'm saying x can be equal or less than 12. So it's anything between 0 and 12, including 12. So 0 is less than x, which is less than or equal to 12. What about this one? Well, the domain here is any real number. The domain here is x is greater than 0. So x is greater than 0 rules the roost, so to speak. It's going to be the one that determines any restrictions. Example 2, same functions. If p of x is f minus I of x, then what is p of 81? Well, just follow this logic, and you're going to be able to write this in a number of different ways. That's what that means. But then p of 81 will be equal to f of 81 minus I of 81. In other words, you're going to find the two y coordinates and subtract them, but you're not really looking at a graph to do so. And I'm going to say to you that finding f of 81 is pretty trivial. You put 81 in, you double it and add 6 and get 166, I think. Minus log base 3 of 81, which is 4. The answer is 162. All right, what about B? We don't need to know that this is I, but I'm just putting it here to remind myself to repair these errors. If R of x is g minus h of x, what's R of 4? Well, R of x is g of x minus h of x. That means R of 4 is g of 4 minus h of 4. Again, I'm not showing my work here. I think it's reasonable, unless it's a written response, that everybody in the room and myself can put 4 in for x in g and see that you get 14. However, having said that, please double check my math. Okay? And then we're going to put 4 in for x in h. Well, 2 times 4 is 8. 8 taken away from 24 is 16. Root 16 is 4. R of 4 is equal to 10. We have one last example, and this is a real thinker. I think, or is there another one on the next page? There is. We'll do the other one on the next page tomorrow. This is going a little long, okay? I think you could do it on your own without, I don't think it's actually a necessary example. I'll show it to you quickly, but I won't do it. So we have f of x and g of x in example 3. And you're asked for the domain of the sum of the two functions. So what this boils down to, everybody, is what is the domain of each function? Let's start off with this function and recognize that for f of x, x minus c must be greater than 0, which means x has to be greater than c. We don't know what c is. There's some number, it's where the asymptote is, that x must be greater than. Let's just park that. On the other hand, g of x has that for a domain, because there are asymptotes there. Not holes, by the way, asymptotes. So what is common? Well, we need to understand what this is saying. This is saying C and D are positive numbers. but D is a bigger number than C. And what that means is that on a number line, we have some position where there is C. D is bigger than C. So we have another point over here that's D. We have another point way back here that's negative D. I mean, D is positive, but that means negative D is negative. And our logarithmic function has this domain. This is for log base b of x minus c. And our rational function has this for the domain. And I don't know that you need to draw this. The rational function has this for the domain. Oops. It has every number except for D or negative D. So where do they overlap? Well, obviously x must be bigger than c, because that's where they're common, but x cannot equal D. Because if it is, even though the logarithmic function is defined at that point, the rational function is not.